Dear students, welcome to lecture number 18, Analysis and Design of Basic BJT Bistable Multivibrator. So again, here is the disclaimer. The information presented in this video is meant to supplement and not to replace the professional guidance or training. So what are multivibrators? Multi means many and vibrator means oscillator. A circuit which can oscillate at number of frequencies is called as multivibrators. So coming to this definition, an electronic circuit that generates non-sinusoidal waveforms such as square, rectangular and sawtooth waveforms is known as multivibrator. So it is basically a switching circuit which depends for operation on positive feedback. So the type of feedback employed here is positive feedback. Stages of amplification. Basically, it is a two-stage amplifier circuit with output of one stage connected or fed back to the input of another stage. Types of multivibrators. So depending upon the manner in which the transistors change the state, the multivibrators are classified as astable multivibrator, monostable multivibrator and bistable multivibrator. Now let us try to understand what exactly is bistable multivibrator. So the bistable multivibrator is also referred to as Eccles-Jordan circuit, trigger circuit, scale of two toggle circuit, flip-flop and binary. So basically it has two stable states. Initially, if the circuit is in state 1, then when external trigger pulse is applied, the circuit is driven into state 2 and remains in that state. When second pulse or second trigger pulse is applied, the circuit changes from state 2 back to state 1 and remains in this state. Thus, each input is used to generate one half of the square wave. So basically, when I apply a kind of a trigger, then let us mark this as T1. So if this is the original state, stable state, then moment I apply a trigger, it changes its state and it goes to high condition. So we can mark this as state 1 S1 and this as state 2. Both these states are stable. So if I want to change or bring out the change in this state, then again I need to apply a pulse, a triggering pulse. So what will happen the moment I apply the triggering pulse, this state 2 will again change to the state 1. From high it will go to 0 or low. So basically in case of a bistable multivibrator, both the states are stable, and if we want to bring out the change in the states, then we have to apply the trigger pulse. Depending upon the timing interval of the trigger pulse, we can derive any kind of pulse output waveform, and it's very easy to generate a symmetrical square wave signal from bistable multivibrator, which actually is difficult to get from a stable multivibrator. So now we'll try to understand the working of bistable multivibrator using a generalized form. So here refer the circuit diagram which is drawn. A1 and A2 are the active devices, and in this circuit considerations we are going to use transistors as an active device. So as you know, the transistor has got three terminals: collector, base and emitter. Likewise, in this circuit diagram we are representing it as X, Y and Z, where X is the input, Y is the output and Z is kind of an emitter terminal. The polarities that have been shown here plus VCC are correct for NPN transistors, and if we are to use PNP transistors, then we have to reverse the polarities. The output of each transistor amplifier stage is directly coupled to the input of another stage. So you can have a look at this circuit diagram. So here this is the output of amplifier A1. This acts as an input to the second stage, whereas the output of this stage, that is the amplifier A2, forms as an input to the first stage. So basically it is a two-stage device that what we have discussed in the previous slide. Now we'll try to understand the working of it. Let I1 here, I1 and I2 be the quiescent current of two stages. From the symmetry of the circuit, it is expected that both the currents must be same. So if you look at the circuit, it's kind of a mirrored circuit wherein this component Ry and here Ry are of same value. R1 and R1 is of same value. So the current drawn by the circuit will be almost similar. So I1 will be equal to I2. Now assume that the current I1 increases. So the two transistors are never identical. So one of the transistor will go into conduction first, and let us assume that the transistor A1 goes into conduction first and I1 increases. So current I1 increases. Due to this, the voltage at Y1 will decrease. So voltage at this point is going to be less. Now why? Now the moment the current is passing through this resistor, there will be a voltage drop across this resistor, and the total voltage at this particular point will be VCC minus of I1 into Ry. And as we have said, like the current I1 increases, so there will be more and more voltage drop across this resistor, and the share of the voltage at this point will be less and less. Now the voltage at this particular point is again connected back, or it acts as input to the second stage through this voltage divider network R1 and RB. So along this path there will be some voltage getting dropped across this R1, and by the time the voltage reaches here, it is very much decreased. Now this decreased voltage forms as the input to the second stage. We are going to use a transistor in a common emitter configuration. So this amplifier will act as an inverter. So the output at this particular point will be inverted and amplified. So the output voltage at Y2 at this point will be more, or it will increase. Now this voltage, will mark this as VC2, is in turn connected to the base of the transistor A1. So this will drive the transistor A1 further into conduction, so thereby increasing the current I1 and decreasing the voltage at Y1. Now this cycle will repeat. The current I1 will keep on increasing and I2 will keep on decreasing, and this drives the circuit away from equilibrium. This happens due to regenerative feedback used, and will occur only when the loop gain of the circuit is more than unity. So when we sit to design the circuit, the gain of the amplifier has to be always greater than 1. There are two types of transistor bistable multivibrator circuits. One is fixed bias transistor circuit, another one is self-biased transistor circuit. In this video lecture, we'll be concentrating on fixed bias transistor circuit. Our actual circuit diagram has been drawn. We have replaced the amplifier A1 and A2 by the equivalent transistor circuits Q1 and Q2. You can check out the collector resistors for both these stages of transistor Q1 and Q2 is same. The output of this amplifier is connected back to the input of the second stage, and the output of the second stage, that is transistor Q2, is in turn connected back or fed back to the input of the first stage. Now these are the points wherein we apply the triggering pulses to change the states. Now let us discuss about the construction. Have a look at this circuit. The circuit uses two NPN transistors Q1 and Q2. For plus VCC, the transistors to be used are NPN. If at all we have to use PNP transistors, then this VCC will have a reverse polarity, that is, it will be minus VCC. The collector of Q2 is coupled to the base of Q1 to resistors R1, while the collector of Q1 is connected to the base of Q2 through another resistance R1. The characteristics of both the transistors are never identical on account of value of HFE, and we cannot have the identical value of HFE because the technology has not been developed to keep the base region equal in all the transistors. because it is in terms of micrometers. Since the characteristics of these two transistors are never identical, hence after switching on the power supply, one of the transistors starts conducting ahead of the another. Now we'll try to understand the operation. Let us assume Q2 starts conducting. So I'll write here Q2 starts conducting. So it is away from equilibrium. So once Q2 starts conducting, the current drawn by Q2 will be more than that of a current drawn by Q1. So due to this regenerative feedback, the current drawn by Q2 keeps on increasing and that drawn by Q1 keeps on decreasing. Finally, this cumulative process drives the transistor Q2 to saturation. So away from equilibrium, this transistor Q2 is driven to saturation and transistor Q1 to cutoff. This is a stable state of the multivibrator. Now the circuit remains in this state till an external trigger pulse is applied at the set or reset terminal. So you can check out here, there is a set terminal and there is a reset terminal. So by applying a proper pulse at these two positions, we can change the state to, as of now, one stable state is transistor Q1 is cut off and transistor Q2 is conducting. That is, it is in saturation. Now, if a positive going pulse is applied at the set or reset terminal, it will drive the transistor Q1 to saturation and the transistor Q2 to cutoff. So thereby applying a pulse, we can change the state. So we can change the state from Q1 cutoff to Q1 to on condition and Q2 to cutoff condition. So this is nothing but the second stable state of the multivibrator. The circuit remains in this second stable state even though we remove the applied pulse. So it will remain in this state till another pulse is applied to the reset terminals. So thus the two stable states of the bistable multivibrator are: first, Q1 is off and Q2 is on. So on in the sense it is in saturation and off it is in cutoff mode. And the second stable state will be Q2 to off condition and Q1 to on condition. Now if I look at this circuit, transistor Q2, so I can derive the output from here. So when this transistor is in saturation, it is conducting. At that point of time, the output voltage will be 0. So we can derive any kind of a pulse signal by periodically applying the pulses at set or reset terminal. Now let us try to understand the design step. The design steps of fixed bias bistable multivibrator. So under saturation condition meaning when the transistor is on, the collector current IC is maximum. Hence, like for example, if I am applying VCC, this transistor is on, so large amount of current is going to pass through this circuit. So hence we have to connect or place a resistor RC here, which must be chosen in such a way that the value of current IC will not exceed the maximum permissible value of the collector current for the transistor. How do we get that maximum value of collector current for any transistor? By referring the data sheet. So RC must be chosen such that IC, that is the current passing through this circuit, is VCC by RC, which is less than the maximum permissible limit. The value of R1, R2 and VBB must be chosen in such a way that in one stable state the current is large enough to drive the transistor into saturation, while in another state the emitter junction is well below cutoff. So here are the design steps of fixed bias bistable multivibrator. For the design purpose, assume that the values of VCC, VBB, HFE minimum and IC set values are known. Now use the following hints to get the design. First point, assume Q1 and Q2 to be an NPN transistors and assume suitable junction voltages depending on whether transistors are silicon or germanium. Now there are two cases here involved. First case is we can ignore the junction voltages. In the sense, if in case of ideal condition wherein we can neglect the junction voltages, we can say VCE equals to 0 and VBE also equals to 0. These are ideal condition. But practically speaking, VCE is near about 0.2 volts and VBE is 0.7 volt. Now this value of VBE depends upon the make of transistor. If it is silicon, it is 0.7. If it is germanium, it is 0.3. So there are two cases involved. First case, we can ignore the junction voltages, and in the second case, we have to consider the junction voltages. The base current of the on transistor is taken as 1.5 times the maximum value. This you will understand when we solve the problem. The current through R2 of the on transistor is taken as 1/10 of its collector current, is kind of a thumb rule. The current through R1 towards on transistor can be neglected, and hence the current drawn from the supply by on transistor can be assumed equal to the collector current of on transistor. So now let us try to understand the design steps of fixed bias bistable multivibrator. Now entire idea here is to find out the unknown resistances. Now for which we have to start with an assumption, and let us assume Q1 is off and Q2 is on. So refer to this part diagram. So you can make out the transistor Q2 is on and Q1 is off. So here is the equivalent circuit. In such case, we can write VC2 equals to VCE set. Now what is this VC2? It is a voltage at the collector terminal of transistor Q2, and since it is on, there will be a heavy amount of current passing through that transistor, through that circuit, so the output voltage will be as good as 0, so which is near about equal to VCE set. Likewise, we can calculate the current I1. So I1 will be equal to VCC minus VCE set divided by RC. So here, if I want to calculate the current passing through this resistor, check out the two ends of the resistor. At one end it is connected to VCC, the other end it is connected to VC2. Now we're going to try to solve this problem for two cases. Case 1, if we want to ignore the junction voltages, we are going to take this VC2 as 0, and if we have to consider the junction voltages, then this has to be taken as 0.2 volts. So this is the incoming point, this is the outgoing point. So it is VCC minus VCE set. So VCE set is the voltage at this point divided by RC. So which is near about equal to IC2. The amount of current passing through this path I2 is very much less, negligible. So I1 is as good as IC2. So we can write here neglecting I2. Now from this equation we can calculate, or we can find out the value of RC. So it will be what? VCC minus VC2. So I'm writing VC2 instead of VC set divided by current IC2, and in the problem statement this IC2 is IC set, which is a known value, which is provided in the problem statement. So we can easily calculate the value of RC. So one component has been designed. Next, now for this case the transistor Q2 is considered to be on and Q1 is off. So this is another part diagram. So now referring to those set of guidelines and point number 3, hint number 3, we can write current I4 equals to IC2 by 10. So as per the point 3 that we have discussed in the previous slides, and I4 is equal to VB2 minus of minus VBB divided by R2. Now, where is current I4? It's over here. Passing through this resistor, check out the two ends of the resistor. One end is VB2, the other end is minus VBB. This is the conventional flow of current. So this minus this particular terminal. So this is already connected to minus of VBB. So the equation is VB2 minus of minus VBB by R2. So which equals to VB2 plus VBB divided by I2. So we can find the value of R2 as VB2, sorry, here it is, kindly make the change R2. So it is VB2 plus VBB divided by I4. So thus R2 is known. So we have already calculated the value of RC. Now we have been able to calculate or find out the value of R2. Now the current through R1 is I3. So I'll write here the current through R1 is I3, and if you look at this point, I3 equals to I4 plus IB2. So there is branching of this current IB2 and I4 from I3. Again, IB2 is 1.5 times IB2 minimum. Now what is the difference between this IB2 and IB2 minimum? IB2 minimum is a value that has been derived using HFE minimum. So this is the minimum set of current which is required to drive the transistor to on condition, because transistor is a current control device. Now practically we have to calculate the value of IB2 and then we have to compare it with the IB2 minimum. If this condition is satisfied, if the actual current which is going into the base of the transistor is greater than IB2 minimum, we say that that particular transistor is driven into on condition or saturation. So from this, I3 is known. So now we can write the equation for I3. I3 is the current passing through this path. So it is VCC minus of VB2 divided by R1 plus RC. Therefore, R1 equals to VCC minus VB2 by I3 minus of RC. So from this exercise, the value of R1 is also known. So thus the final design can be obtained. Just make a note here, for the PNP transistors, the supply polarities must be reversed, and accordingly the changes must be made using the above mentioned equations. So now we'll try to understand the actual numerical. The fixed bias bistable multivibrator uses following parameters. VCC is 12 volts, VBB is minus 8 volts, R1 is 10 kilo ohms, R2 is 50 kilo ohms, RC is 2.2 kilo ohms. The transistors are silicon transistors. So whenever this word appears in numerical, then you have to note down the voltage which is required to drive the transistor to on condition. If it is silicon, this voltage has to be 0.7 volt with a minimum value of HFE as 30. Calculate the stable state current and voltages when. Now there are two scenarios here. One, all the junction voltages are neglected, and second, assuming VC is set as 0.2 and VB is set as 0.7 volts. Now what we mean by this point, all the junction voltages are neglected. So if I take a transistor as a switch then let us mark this as VCC. There is a resistor, the other end is connected to ground. So if the transistor is on, then heavy amount of current passes through this device, the output voltage is considered to be as 0. So we say the VCE equals to 0. And next VB set equals to 0.7 volt. Now this is the typical practical values. Ideally we assume that the transistor is on for a value VBE equals to 0 volt. So these are the conditions when the junction voltages are neglected. Otherwise practically this value has to be 0.7 and this value has to be 0.2. Fine. So we'll start with the first case. Case 1, the junction voltages of on transistors are neglected, that is VC2 equals to 0 and VBE2 is also equals to 0. Now since emitter is connected to ground, we need not write it explicitly here. So instead of that we can write it as VC2 and VB2. So we'll solve this problem step by step. The first step, to verify whether the transistor Q1 is off. We have started with the assumption that transistor Q1 is off and transistor Q2 is on. Now we have to make sure that the transistor Q1 is indeed off. So to understand this concept, we have to draw the equivalent circuit as shown in the figure. So transistor Q1 is off, so we neglect all those sets of associated circuitry with it, and transistor Q2 is on. On meaning there is a proper flow of current. We have to have a proper path for that current to pass through it. Okay. Now with this understanding, first of all we are going to check what is the voltage at the base of transistor Q1. So here is the transistor. I'll just redraw it here. So this is the transistor Q1. We have to check out what is the value at this point. So let us mark this voltage as VB1. So the voltage over here, the set of equation will be VB1 will be equal to minus of VBB R1 upon R1 plus R2. So this is minus of 8. R1 is 10 kilo ohms. So just write here R1 is 10 kilo ohms. RC is 2.2 kilo ohms. R2 is 50 kilo ohms and VBB is minus of 8 volt. This is given the problem statement. So it is 10 divided by 10 plus 50. So the value is minus 1.33 volt. Now what is this value? This is the voltage present at the base of NPN transistor, and as VB1 is less as compared to VBE, that is 0.7, it ensures that the transistor Q1 is off. Next step. So again we have assumed that the transistor Q2 is on. Now we have to make sure that the transistor Q2 is indeed on, for which we have to calculate the value of IC2 and IB2 minimum. Now what is IC2? Look at the figure. IC2 is the branching out of current I1. So I1, look at the figure, I1 is branching out as I2 and IC2. Fine. So first let us calculate the value of I1. So I1 equals to VCC by RC. Now I want to find out the value of I1. What is I1? It is the current passing through this resistor. Check out the two ends of the resistor. One end is connected to VCC. What is the other end connected to? VC2. Now actually the equation is VCC minus VC2 divided by RC. But then we are neglecting the junction voltages. So this VC2 is equal to 0 volt. So it is as good as connected to ground. So the equation is VCC by RC. And if I substitute the values, VCC is 12 volt and RC is 2.2 into 10 to the power 3. So the answer is 5.45 milliamperes. So likewise we are going to calculate the current I2. So the current I2 flows from in this path. So this is the initial point VC2 and it goes up to minus of VBB. So I2 will be 0, that is VC2 minus of minus VBB, the other end for conventional flow of current, divided by R1 plus R2. So if you substitute the values, so it is VBB is minus 8, so minus of minus is plus 8 divided by 10 plus 50. So the answer is 0.133 milliamperes. Fine. Now what we are interested in is finding the value of IC2, and that we have discussed IC2 is nothing but a difference of I1 minus of I2. So let us check out how much is that value. 5.45 minus 0.13, so it is 5.316 milliamperes. Okay, now we have to calculate the value of IB2 minimum. Now this IB2 minimum is a function of IC, that is collector current, and since we are dealing with the transistor Q2 here, it is IC2 divided by HFE minimum. Fine. IC2 is 5.316 milliamperes and HFE minimum is 30 from the problem statement. So the final value of IB2 minimum is 0.177 milliamperes. So this is IB2 minimum. So what is the significance of this IB2 minimum? Now from the next step we are going to calculate the actual value of IB2. Now that is the value which is required to make the device on. So that value will be compared with IB2 minimum. So it has to be always greater than IB2 minimum to make the device on. For example, if you get IB2 as 0.15, so in that case 0.15 is less as compared to IB2 minimum, so that current is not sufficient to make the device on, isn't it? So now we are actually going to find the value of IB2. So next step, calculate the actual value of IB2 and verify that IB2 is greater as compared to IB2 minimum. RC is, I'll just write down the value. RC is 2.2 kilo ohms. VCC is given as plus 12 volt. R1 is 10 kilo ohms. IC, this transistor is off, so IC1 is 0, is already listed. Then this value, transistor is on, and since we are neglecting the base voltages, junction voltages, so this value will be 0 volt. The value of R2 is given as 50 kilo ohms and VBB is minus of 8 volts. We have drawn the equivalent circuit. Now we'll proceed to find out the actual value of IB2. Now if you look at this circuit diagram, the IC1 is 0, so this current I3 will flow here in this direction. At this point there is a branching of current I3 as I4 and IB2. Fine. With this background information, we'll continue with the numerical. Now I3 is the current through RC and R1. Is the current through RC and R1 as IC1 equals to 0. Why it is 0? Because the transistor Q1 is off. Now we can calculate the value of I3 as VCC divided by RC plus R1 and as VB2 equals to 0 volt, neglecting the junction voltages. Fine. So if we substitute the values, what we get is I3 equals to 0.9836 milliamperes. Fine. I4, trace the current I4. It flows from here, this point, to minus of VBB. So I4 will be VB2. It always start from the conventional flow of current, minus of VBB. This is minus, divided by the resistor along its path is R2. So it is 0 plus 8 volts divided by 50, and the answer is 0.16 milliamperes. What we are interested in finding is the value of IB2, which is nothing but a difference of I3 minus of I4, which equals to 0.8236 milliamperes. Now the problem does not end here. We have to compare IB2 with IB2 minimum. And how much is the IB2 minimum? IB2 minimum, we have already calculated it as 0.177 milliamperes. And what about IB2? What we have obtained is 0.8236, which is greater than IB2 minimum. So the transistor, you understood this, IB2 is very much greater as compared to IB2 minimum. So that will ensure that transistor Q2 is in saturation mode. So our assumptions are correct. Q1 is off and Q2 is on. So we can calculate the value of VC1, VCC minus of I3 into RC. I3 is the current passing through this resistor. So the total voltage drop across this resistor will be I3 into RC, which is subtracted from VCC. The difference is the voltage at this point. So let us calculate. So VC1 equals to VCC minus I3 into RC. So this is 12 minus 0.98 equals to 9.83 volts. So this is the value of VC1. Next, we have to simply tabulate the results what we have got. The value of IC1, since the transistor is off, it is 0 amperes. IC2, we have calculated it as 5.316 milliamperes. IB1, the transistor Q1 is off, so naturally there won't be any questions of base current, so it is 0 amperes. IB2 is all important parameter, which we have calculated it as 0.8236 milliamperes. VC1 just now we have calculated, it is 9.836 volt. VC2, since the transistor Q2 is on, the output voltage is VC is set, and since we are neglecting the junction voltages, it is 0 volt. VB1, the very first step what we have calculated is 1.33 volts, and VB2, again neglecting the junction voltages, VB2 is 0 volt. Clear? There is another parameters which is normally not asked in the exam, but for your information, there is something called as output swing, which is denoted as VW, which is given as VC1 minus of VC2. So VC1, what we have got is 9.836 volts minus of 0 from here. So VW voltage swing is 9.836 volt. This is the final answer. So we have come to an end of the first case, first scenario, neglecting the junction voltages. We have to follow the same steps when we consider the junction voltage. That is, VC set will be taken as 0.2 volt instead of 0, and VB set will be taken as 0.7 volts instead of again 0 volts. So we'll start with the second section. Let us mark the values. VCC is 12 volts. IC1, this on voltage, earlier we had taken it as 0, but now we have to take this as 0.7, and this voltage we have to take it as 0.2 volts. VC set given it as 0.2 volts and VB set is 0.7 volt. For the transistor Q2, for this transistor Q2, the emitter is grounded. So we can simply write, instead of VC set, we can write VC2 as 0.2 volts and VB2 equals to 0.7 volt. So referring to this figure, now you can make out what is the first step. The first step is to check out how much is the voltage at this point, at the VB1. Fine. Now here in this case, the VB1 will be due to both VBB as well as VC2. In earlier case, we have ignored this as, we have taken this as 0. So this voltage was not having any kind of effect at this point. But now, since although it's very small, but it will have some kind of effect at this point. So now VB1 will be due to VBB and VC2 as well. So we have to make use of a superposition principle. It's about considering the effect of each voltage source independently. So when I want to understand this, so VB1 will be equal to minus of VBB into R1 divided by R1 plus R2 when VC2 is considered to be 0 plus VC2 into R2 upon R1 plus R2 when VBB is considered to be 0. So we have to consider two scenarios and then add them up. First scenario, set VC2 equals to 0. Second scenario, set VBB equal to 0. This is superposition principle. Now if I substitute the values here, this is minus 8 divided into 10 divided by 10 plus 50 plus VC2 is 0.2, that is VC set, into 50 divided by 10 plus 50. So if you solve, the answer is minus 1.16 volt. I think for previous problem it was previous case it was minus 1.33. Now it is minus 1.16. So you can make out due to this VC set value, this is slightly reduced. So we can make a comment that as VB1 is less as compared to VB cutoff, hence transistor Q1 is off. Current I1 equals to VCC minus VC2 by RC. Substitute the values, 12 minus 0.2 divided by 2.2. So the answer is 5.36 milliamperes. The steps are similar, only thing like we have to consider the junction voltages. So I'll keep on solving. I2 will be equal to VC2 plus VBB divided by R1 plus R2. If substitute the values, what we have interest in finding is IC2, that is difference of I1 minus of I2. 5.223 milliamperes. Next, IB2 minimum is IC2 divided by HFE minimum, IC 0.174 milliamperes. This is the minimum value of current which is required to make the device on. Now practically, just what we have solved in the first scenario, first case, we have to follow the same steps. We have to actually find out the current entering into the device. That is what is referred to as actual IB2. So to calculate IB2, refer to the second figure that we have drawn. In that case, we have to set now VB2 equals to 0.7 volts. So in that case, I3 will be equal to VCC minus of VB2 divided by RC plus R1. Substitute the values, 12 minus 0.7 divided by 2.2 plus 10, and the answer is 0.926 milliamperes. I4 equals to VB2 minus of VBB divided by R2, so it is 0.174 milliamperes. From I3 and I4 we can calculate the value of IB2. It is I3 minus of I4, and the answer is 0.752 milliamperes. So now we have to compare IB2 minimum with IB2, and you can make out that IB2 is greater as compared to IB2 minimum. So this makes the transistor Q2 to be in on condition, that is saturation. Let us calculate the value of VC1. Refer the figure. VC1 is the voltage across the collector terminal of transistor Q1. So it will be VCC minus of I3 into RC. VC answer is 9.9628 volts. So here we have to tabulate the final results. IC1 is 0 milliamperes because the transistor is off. IC2 is 5.223 milliamperes volts, and VB2 is 0.7 volt. What about the output swing? It is VC1 minus of VC2 denoted as VW. So it is 9.7628 volts. So with that we have come to an end of this numerical. Let us summarize the applications of bistable multivibrator. So it is referred to as flip-flops, and you know flip-flops are basically used to store the information. So it acts as a memory element in shift registers, counters, etc. It is used in processing of pulse type waveforms. So by just controlling the timing of pulses, we can generate any kind of a pulse waveform with a different t-on or a duty cycle. It is used for the performance of many digital operations like counting, storing of digital information. Next point, used to generate the symmetrical square wave, which is not practically possible with a stable multivibrator. And how can we do that? By triggering pulses at equal interval, and it can be used as a frequency divider. So these are some of the review questions for you all. If you refer the past semester exam question papers of Goa University, once a question has been asked on this, with the help of circuit and waveforms, explain the operation of bistable multivibrator. So you start with the definition, circuit diagram, construction. You have to stress on the waveforms, particularly here, and the operation. It was asked for 10 marks. So with that, we have come to an end of the discussion on bistable multivibrator. If you have any difficulty in any doubts, you can post them in comment section. Thank you.